Thank you for the introduction. So this talk it has a rather long title, but let's look at some words. We have interactive visualization and segmentation. Let us look at the main motivation we had. So I'm from VRVis Research Center, so I'm more in the visualization area. Let's look at what we envision to have. We have high quality volume visualization of this casting part, for example, whereby the inclusions and pores can be visualized separately. Here we have different colors for different properties of the detected features. For example, the small detections here are red. So, well, this is well known, and there's software to accomplish this kind of stuff, but at the end of the talk, you'll hopefully know why we did it differently. So, if we look at the standard workflow, in order to get to such pictures, we need some segmentation algorithm. For the algorithm, we need to find some parameters. We do this, then we run the algorithm, and then we get some results. Next, we can feed those results into the visualization in order to get the images out of it. Unfortunately, there is also parameter tuning involved in order to find the right parameters for the algorithm. So basically, we need a good algorithm, and we need insight in the parameters of the algorithm in order to get good results. If we look at kind of problematic data sets, like here, we have a rather complex geometry, we have CT artifacts all together, and we could now use a rather good algorithm and know the parameters, or we can go for a simple algorithm. If we look at the situation here, we have those kind of gradient on the intensities, although the density of the material is the same, and this is a problem for the algorithm, of course, if we use simple thresholding-based approach in contrast to the previous talk, for example. What happens if we use this? We here have a aluminum sandcast part which gas-induced pores. This is our test part for the evaluation as well. What we can see here is that we have again this intensity gradient, and if we use thresholding, we have low detection rates in the upper areas with the low diameters, and we have noise and false detections in the lower part of the part. So what can we do about this? There was a talk of a colleague of mine several years ago, also at this conference, where they used parameter space exploration in order to sample the input range of parameters for the algorithm. Later, people more worked on different algorithms in order to use the different algorithms for the same data set in order to get the best results. So here, the workflow kind of changed because we choose the parameters, we run them with several algorithms, then we get many results, and then we inspect them. So this is kind of better. There is recent research in that area, also, of course, from colleagues in the audience. So what are the challenges if we go to big data in CT? If we use a good algorithm, of course, we kind of get good results with local adjustments and stuff like this. But if we go large in size, like if we have a 4K detector, we quickly arise at more than 100 gigabytes of data size, and then we're kind of out of luck if we want to try several algorithms with different parameters. Then we kind of have this long round trip time, and we can't get our work done. So is there a different way? This was kind of the naive vision we had. Have a kind of a fair segmentation method which works reasonably well, and then give the difficult decisions to the user, involve the user of the segmentation method in order to guide the algorithm towards a good solution. This was kind of the main idea. So we really, in contrast to the previous talk, took a rather simple approach and used region merging technique for segmentation, which can be implemented rather efficiently on the GPU. For that, we based our approach on statistical region merging, whereby we did some estimation on the standard deviation we need in order to adjust the thresholds. So this is kind of state of the art, but we experimented with those rather old approaches. What can you expect if you use such segmentation method? If we again use our aluminum cylinder here, we see in the upper area, while we had no detections previously, if we used the wrong threshold, now we get results, but we kind of get over segmentation. If we now modify the parameter and run the algorithm again, we end up with under segmentation, although in the upper areas now they didn't fall apart, the features, right? So we can find a parameter set in order to make this work. So either we improve on the algorithm, or we take a different approach. And the way we went here is we live with over-segmentation. So we run the algorithm, which is fast. Then we have an over-segmented image, and then we ask the user to remove features which are unwanted in order to go back to the algorithm. So the envisioned workflow then is we run an analysis, we let the user explore intermediate results, tweak some parameters in between of the running algorithm in order to come back to the algorithm and improve further. For this we implemented a research tool. I want to show you live. So here you have different views. We have a direct volume rendering 3D view up there, and here we have the slice view. So this is not standard software. This is our research tool. What I can do now is I can run the segmentation. This is all running on my laptop here, which I didn't even plug in. However, it uses this rather simple segmentation method, and we arrive with a kind of okay solution. For this dataset, it's rather okay because it's not that nasty, the dataset, right? But if we look at the results, I need to explain. Here we have the direct volume rendering, and here we have a parallel coordinates plot, which shows all the features we found. All those Smarties here are the different features we found, are put there we compute several properties, for example, the feature size, the sphericity, the average value, and the standard deviation of the feature we found. And now we're in this stage that the user can use those filters. Here we have kind of a window we want to filter for in order to here you see the inclusions here now. So this is the basic setup, right? Let's now switch to this nasty data set I talked before. Load the data set. This is now 1000 times 1000 times 500 boxes. And here we have again our nested data set. What we can do now is, again, we run the segmentation process, which basically is rather simple because it only uses this single threshold, which defines how likely we would like to merge neighboring regions. And again, this is now, it's computing the result, which might be kind of okay, but as you can see here, we have different regions. We have large regions here, and then we have smallest, and then we have all those little pores, right? What we can now do is we can look for different sizes. This is the background, then we have the part, and then if we move lower, we move our filter to the lower area, suddenly the pores arrive. So we have pores of this specific size I just selected. What's interesting here is that if I use an average filter, you can see that now within this range from 0.125 to 0.35 of density, normalized density. We have this window here, and we can now move this window and say, okay, if you move down, the features in the upper area here go away, and in the lower area they arrive because of these inhomogeneous intensities we have from the CT artifact. So what we can do now is we can look for different parts. For example, we can filter out the background. For the algorithm, it's hard to decide if it's background or if it's a pore. So if we now remove the background and unwanted features, we can jump back into the algorithm and proceed. For example, here we have some unwanted artifacts here, like such wrong detections, and we can, for example, filter them out by using the sphericity if we are looking for features of which look like pores. Right? Now we remove them, and now we are in a state that we have a rather okay segmentation, and we can go back to the merging step in the algorithm. We perform the merging step, which again can either just merge neighboring regions or use some advanced merging criterion, which can be computed at that time. So now we're in this final situation that we managed to have a rather fast segmentation, whereby we used some user input in between in the segmentation process. What's interesting here is, yeah, we can go in here. We have all our pores. Now not colored that nice, but each pore has a different color now. Interestingly, this thing also runs in the browser, so it's easy to work also in remote areas with it. So let's go back. If we look at what we have achieved. Oh, sorry. We managed to get rather good results for nasty CT scans with a lot of artifacts, which results in images like this. Next, we looked at how does it compare to ground truth, right? For this reason, we used this aluminum cylinder, cut it, then we polished it and used metallography in order to evaluate the result. Next, we aligned it with a slice. We marked it with a cut in order to find the slice, and then we compared the detected pores, and we were quite happy that they match up pretty well. What's the performance of this thing? Here we have the number of voxels, and here we have the time in seconds on a GPU, which is better than this one here. And if we look at the bigger data sets here, we have 2K times 500 times 1000, which is approximately 1.8 gigabytes in 16-bit. We here have 14 seconds of processing time. Then we need to have user interaction, then again just 14 seconds. So what are the conclusions of this method? It's basically we used a rather simple segmentation method, but let the difficult decisions to user. So we presented the intermediate result of the analysis to the user in order to filter out features which are not which we do not look for, and then we let the algorithm continue. In this way, we get rather good results with kind of minimal user input. The question is to present the user the right questions in order to guide the algorithm to better results. So what are the future plans here? We want to investigate multi-material, we want to investigate on regions of interest, and of course we're interested in collaborations on that matter. there's a video, because just the paper is rather is not that it doesn't explain the things like a video. And here we have a link for the video in the upper area. And this is another thing. Our group, or members of our group, just started a startup which is working with CT data and visualization of CT data, and we're working on a virtual reality setup for CT data so that you can move into CT data and look at inclusions in reality. So here we have, this is a huge inclusion in a data set, and if you use this VR headset, you can just walk into this. So just there's those two links, and this might be interesting to look at.
Okay, thanks. We have 3 minutes for the question and the comments. Okay, yeah, the center.
Congratulations on this great presentation. Thank you very much. Could you compare what you are doing with the other approaches for advanced segmentation using different neural networks? Because apparently, in the case that you showed, we could also train the network to detect the pores in most different situations. But of course, there's a lot of labor involved in doing the training. But have you also worked with different neural networks in this approach of yours, or can you compare this, please?
Yeah, I mean, one could, but at this point we used human intelligence instead of artificial intelligence, and we didn't investigate on this further. But yeah, this might be an interesting idea.
Okay, any other questions or comments? Yeah, the second row center.
If I understood well, you found that there is an improvement in detection of pores that are small compared to the normal methods. That's correct? Sorry? You observe an improvement with your method in detection of very small pores compared to the traditional method?
I would say if I have unlimited time and I take the best algorithm, the best algorithm would get the same results or better results. So this is more it's more for having a good result in reasonable time, because you have just 20 seconds and you get segmentation, or you get your images. And the interesting thing here is that you don't have this fully automatic, hard to work with algorithm with very many parameters. You go a completely different way. You take the simple algorithm and you get okay results because you have user insight and expert knowledge you can plug into the algorithm. So yeah, a fully automatic algorithm is nice, but here we just go a different way and don't take the.
And what would be then the limit of pore detections in terms of voxel size, like 2 voxel size or diameter, or 8 voxel size? Or do you see any limitation in terms of?
Yeah, technically, it's just a sampling question, right? How small pores you can count as pores, and
yes.
We typically we do no blurring of the input CT, so we work with the plain data. So if we look at it like this, we can find rather small pores because we have no smoothing involved. But still, in the lowest resolution, like one voxel size, we can't speak about pores, of course, right? Okay. But it works really good for small pores because we work with a complete resolution.
Thank you.
Okay, we have time limitation, so yeah, thanks to speak again.
So the next talk